Hello, and thank you for joining us for this week's Ask Joe webinar. This week we'll be discussing the GNSS elevations, and with that, this topic, it creates a lot of head scratchers in the GNSS surveying world. It's probably one of the biggest questions that I know I get on a normal basis. So the goal of today's webinar is to remove some of the confusion around the subject, and if questions remain, please, at the end of the presentation, ask Joe. Talking today is Joe Sass, and after the presentation, he'll be answering any questions that you have. A little background on Joe, for those of you who don't know him, he is our channel development manager, and as a field application engineer, he is a liaison between product marketing, sales, and engineering. He has a degree in geography, blends nicely with his love for surveying. Since 1998, he has been active with the California Land Surveyors Association, out where he lives. And in 2004, he began representing us with the RTCM Standards Organization, and he currently sits on the board of directors. So with that, I will turn it over to Mr. Sass, and thank you for joining us.
Thank you, Mr. Binder. I'm hoping everybody can hear me. Thank you for attending today. Pretty lofty goal to explain GNSS elevations. I am in no way an expert, but I am very fascinated with this topic. When I got into business 20 plus years ago, I realized that there were two things that were very complex and therefore interesting to me. One of them being antennas and elevations in GNSS sense, and coordinate systems. And so I like both of those, and so we'll just talk through some of these points today, and hopefully I'll shed a little light on a complex topic. So, what is elevation? Elevation is some place that's marked above sea level. And we'll talk about what sea level is later, but that's elevation is related to sea level. And then when we talk about height in a GNSS sense, because this is the topic is GNSS elevations, height is how high or low a place is above or below the ellipsoid. And the ellipsoid is a perfect model that is a best fit of the real shape of the Earth. So, like with the total station, do GNSS heights need to be corrected for curvature and refraction? And the answer is no. They're not affected by light and the bending of light, but they are affected, elevations are affected by gravity. And that's something that's relatively new to our world of knowledge. Probably we've understood that gravity had an influence on elevations for the past 25, 30 years. It's relatively a new science, and there are just a handful of what we call geoidologists in the world that try and understand these corrections from gravity. And how do we do that? We do that through the use of geoid models. We convert the GNSS heights, which know nothing about gravity. We apply a geoid model to these ellipsoid heights, and then we can derive our local elevations, which are in somehow related to a local sea level. So how does it work? The real language of GNSS assumes what they call a hypotheoretical center of the Earth. And it's hypotheoretical because we can calculate it, but we can't go there. So we know where the center of the mass of the Earth is, and the GNSS system is based against that. By the way, that's a secret. The government does not let us know. JPL believes that maybe they have that centroid location down to about the size of a softball after 30 years of observing GPS, but we really don't know for sure. The government does. Anyhow, I took off the decimals here just to make a point about this. When you're using these Earth-centered, Earth-fixed Cartesian coordinates, you hold up your right hand and your forefinger and your thumb, you will describe the shape of those red lines that I show on that graphic. As I mentioned, the x-axis is coming out somewhere west of Africa in the Atlantic Ocean. The y-axis is somewhere south of Sri Lanka, and the z-axis is coming out at the North Pole. And so by looking at these numbers here of these different cities and their numbers of meters, there's a couple of things that you might notice. Number one, the only one to me that's obvious is the z-axis. We can see that the top 6 cities are north of the equator, and Sydney Australia is south of the equator, and it's the only one with a negative number in that z-axis. Makes sense looking at the diagram, but otherwise you have to understand quadrature and which quadrant you're in. You see London there is very close to the prime meridian, which is what the x-axis is based on, so that's why we have a very low number there. But it's still very difficult to tell where Honolulu is just by looking at that XYZ. So we have a way of converting XYZ perfectly. There's no loss of fidelity in the data to latitude, longitude, and ellipsoid heights. So, as I mentioned earlier, ellipsoid heights don't really tell us much about sea level without a geoid model. But now, if I say 21 north and 158 west, we can at least imagine where Honolulu is, because the latitude and longitude language makes more sense to our brains, I think, than the ECEF coordinates. Another thing that this conversion does for it is it separates the elevation from the horizontal. So now we can deal with ellipsoid height by itself, and we can treat the latitude and longitude separately. So it's very convenient. If you'll notice down there in the lower right-hand corner, I show you the tool. It's a National Geodetic Survey tool that I used to convert these XYZ coordinates to latitude, longitude, and ellipsoid height. So this is the equation. You'll see this equation over and over and over and over and over in textbooks and reference and examples and presentations. Mine is no exception. It's a relatively simple formula there. We take the orthometric height, and that equals, to get the orthometric height, and we'll talk about what orthometric is. Let's say for now it's sea level. To get the orthometric height, you have to have the ellipsoid height, so that's the GPS reading, and then you have to apply your geoid separation, and that's the minus geoid height n. Most of us are math savvy, so I think this formula makes sense. I'll work it through though. So if we look at this example, I just worked through that same formula from an Opus example. This was a solution I got on an Opus reading. So it provides me with that ellipsoid height and that orthometric height. It tells me what geoid model was used to compute that separation. And then I just worked through that example. Orthometric height equals ellipsoid height minus geoid. There you see those numbers. In all of North America, except Alaska, I believe, the geoid separation is always going to be a minus. So we're living below the ellipsoid. And so that, in effect, a minus minus a minus is a plus. And so that's how we come up with our orthometric height, which you can see in both my solution of the formula and the solution from Opus. Visualize what the geoid looks like. What you're looking at is gravitational potentials, right? We used to think that all the oceans were the same elevation. They're not. If I were to stand at the beach in Santa Monica, stand at the beach in Anchorage, and stand at the beach in New York, I get 3 different GNSS elevations. If I could stand at sea level at Grand Teton National Park in Wyoming, I'd have a 4th elevation. So everywhere we've got gravity, which is the entire planet, that gravity varies. And this is just a visualization of that gravitational undulation, we call it. So essentially, orthometric and mean sea level are the same, but mean sea level is really a local thing. And I got this information from the Esri website. I thought it was very interesting that, you know, the sea level in Spain is not the same sea level that Canada uses. And that's why we have locally defined vertical datums that differ from each other. So essentially, orthometric is GNSS related, where we apply this geoid model, and that may or may not equal the local mean sea level from the local tidal gauges that don't take into account the bigger world. At least today, probably most of our audience, I would imagine, are Americans, North Americans, and in the U.S., it's interesting. All of our vertical elevations are derived from a point that's in Canada. This is a picture of the pump house inside Rimouski Point, Old Father's Point, it's called. It's in Canada. It's in the province of Quebec. And the National Geodetic Survey, way back, I think, 1998, was Dave Zilkowski. He's retired now, but a brilliant man. He decided that he wanted all of our elevations to begin there, and then he could push south and west from there. It was a place that was it was outside the eastern boundaries and the northern boundaries of the continental US, and he could push everything in one direction. And so that's where our elevations come today as it relates to our current datum, which we will talk about in just a minute. But it was also interesting that, you know, this old man's point has been around for a couple of 100 years, I believe. And so we've got these tidal epochs, many of them, that we can observe. And so this was another reason for choosing this point for the vertical datum of North America, was the fact that we have such a long history of information with this point. Someday I'd like to make it there, visit it. So we've come a long ways, and interestingly, you can see there's some type of what looks like maybe an EDM shot between these two satellites. Well, that EDM, I'm told, is nearly identical to what we have in our total stations today. And these two satellites are flying a couple hundred miles apart, and they're regularly taking measurements between each other. And as they enter an area where there happens to be more gravity, the lead satellite will dip down. It'll be attracted closer to Earth because of that increase in the gravitational fields. And because of then this change in geometry between the two satellites, we can measure those angles, and we can detect those distance changes. And that's how we've mapped most of the gravity fields in the US. This is a polar orbit, and it's we're on Grace 2, I think, right now. And the follow-on to this is going to be what's called GravD, which is another mission of the National Geodetic Survey to map our gravitational potentials. And what they're finding is that even those gravitational potentials are changing. So they want to lock these gravity changes into an epoch, a period of time. More to come. So what else affects elevation when you're using GNSS besides the calculation of getting, you know, from GNSS heights to local elevations? We have the actual system itself. And really, I left all the lines here because they represent different dilutions of precision. That's what DOP stands for, dilution of precision. So in that case, the lower the number, the better. And you'll notice how flat that bottom line is, the horizontal dilution of precision. And the reason it's so flat with very little jags in the mark, and the reason why it's got the best figure there, the lowest dot, is because we can see satellites around us 360 degrees. We've got great geometry. They're at all elevations around us, and we can see, like I say, if you're out in the middle of a grassy field with no obstruction in any direction, you can see all 360 degrees. If you look at the line above it, though, that's the vertical dilution of precision, and you can see there are a lot of jags there. And there are times when vertical precision is diluted, and that's strictly related to the geometry of the satellites. So number one, you can see that in all cases, vertical dilution of precision is worse than horizontal. And the simple reason is that I don't read satellites below the horizon. I can only read them down to the horizon. Most of us use an elevation mask, so we're masking off the last 5 degrees of the horizon. So if we could be like in space and measure down below the horizon, then our vertical dilution of precision would probably get a lot better, because we would then be able to get some real three-dimensional geometry in that vertical dimension. And if you were to relate the vertical dilution of precision you saw on the previous page to the relatively low areas, like down in here, if you can see my mouse, this is where we had high VDOP, and that's because we don't have these high satellites. So when I'm looking at a plot of the elevation of the satellites, this right here, over here, right below the globe, probably going to be an excellent time of day to make vertical measurements, because I've got 2, 3, 4 satellites that are very high in the horizon that are going to help me lock in that vertical aspect. Notice again that the spec, and I wanted to explain the spec. So again, we're almost twice as good in the horizontal element as we are in the vertical element. And this ppm is distance from your base station. So for every kilometer of distance I'm away from my base station, I'm going to add another millimeter of error. There's a million millimeters in a kilometer. And so I'm 10 kilometers from my base station. I've now introduced a centimeter of error, or 3/100 of a foot of error. This is imaginary. Notice that I've said imaginary. As a satellite travels through the horizon, or from horizon to horizon, travels its orbit above a typical antenna. An imaginary ideal antenna would have 0 phase center variation. And this is a term that's common in our industry, PCV, phase center variation. And then you also notice antenna reference point. And these are two very important and very different places on a GNSS antenna that need to be accounted for. Because in real life, a real antenna does something like this, right? As the satellite travels from horizon to horizon, the phase center variation varies. So if I had a phase meter hooked up to that antenna as the satellite's passing through, I would see this phase center variation in a real antenna. And what I don't show you in this graph is L2 and L5 and the other satellites that are now in space with the other constellations. It makes for a very complicated phase center variation pattern that must be accounted for if you hope to get good elevations. Back in the day, it wasn't as important. When we set up our own base and our own rover, we could, as long as they were both doing the same, we could trust it because the antenna phase center variation was identical, so that it would cancel each other out. But in today's world of network RTK, we don't know what antennas we've got on the other side. We need to correct for the antenna we've got on our side. I wanted you to notice here that the National Geodetic Survey calibrates. This is the mecca for GNSS antennas. Every manufacturer sends 3 of their antennas before they're released to the NGS in Corbin, Virginia, and they put them on this pillar, and this pillar measures all of the satellites and all of the different combinations of patterns, and the NGS then creates a file that describes these phase center variations so that we can normalize our GNSS elevations to the antenna reference point, which does not move. You can see that on a Spectra Epoch 35, there's 3.93 inches to get to the phase center variation. And if you took a tape measure that far, 4 inches above the antenna reference point, you'd find that you're outside the plastic of the antenna. So the phase center of this antenna is actually above the plastic, the blue plastic you're seeing there. The NGS, as I said, manages these definitions. In the recent past, they had what they called relative antenna calibrations, and they have moved now to absolute antenna calibrations. The relative just took into account what happened right there, but it didn't take into account distances, for instance, in the attitude of the antenna, and it didn't take into account the azimuth dependency of the satellite. So now with today's absolute antenna calibration list, and you can see I've dropped it down there on the NGS website, these absolutes now account for both the elevation of the satellite and the azimuth. So, as I explained at the very beginning, global lat long height is really ECEF, but we'll talk just global lat long. So global lat long height is what's coming from space. It's a datum that's been defined by the US government in the case of GPS, and most of the other constellations have agreed and followed that same global datum that's coming from space that assumes the same hypotheoretical center of the planet. When we apply a datum, that's where we actually normalize it to our country. In the case of the United States, that would be NAD 83 today. NAD 83 is based on the GRS 80 ellipsoid. So here we've applied a datum by using a local ellipsoid, not the WGS84 ellipsoid, but the GRS80 ellipsoid. And from there, we then project it into our local system, in my case, California State Plane Zone 6. If you're in Wisconsin, you have 300 different projections to choose from, or soon to be at least that many. Close. I'm kidding. They have 120 different projections at least to choose from in the state of Wisconsin. We take that projection, we get our grid north, grid east, and then we deal separately with the geoid aspect, or the Z element of the calibration. So how do we actually take this concept that I've shown you here and make it into survey points that we can use? And the safest, most common method for turning global coordinates into local coordinates is through the site calibration technique. And even if you don't understand a thing about what I've said on the left, all you have to do is understand what I say on the right, and you don't need to know what's on the left. The only thing you would have to know about the right side here, project area, is that size is limited. Let's say 40 kilometers by 40 kilometers at 1,000 feet above sea level. And I'm just roughing it there, but because of this element here where we apply a map projection, anytime we apply a map projection, we introduce some type of distortion, right? It could be distance, it could be angles, it could be shape, but there's error. And in most software packages today, if we're trying to localize to a 5,000, 10,000 system, this projection right here is an oblique stereographic projection, which has distortion in all of the aspects, but it's minimal and it goes out pretty equally from the center of your project area. So that's how we handle this. And if you were interested in that, on most of the software packages, you can dig into the details of your site calibration and see that an oblique stereographic projection was applied at this point in this graph. So if I have one calibration point, let's say that's 5,000, 5,000, I can let my software assume the rest. Okay, give me scale and give me north, right? The north is going to be a geodetic north rotation based on our current ellipsoid and projection definition. And it's going to be scale 1, so it matches my total station. That's a great way to go if you don't have any control on the ground and you just want to assume coordinates. Survey Pro, for instance, my software will let you do that quite easily. Most of the time we have more control on the ground than just a single point. Going back to the comment you may have seen from Phil Stevenson, a previous colleague of mine, what he meant was, by his comment, the proof is in the dirt, is that these calibrations have to occur at some point where the prism pole point is touching the dirt or the point on the ground. You can theorize a lot about this, but at some point you have to actually go out there and measure it. And one of the interesting things about the Trimble coordinate system library, that CSD file that we might be familiar with, is that all of those coordinate systems have been proofed. The proof has been seen in the dirt. That's a different story. So right here, if I have 2 points that I use for my control and I want to site calibrate to my 5,000, 10,000 system, this right here is fine, but it's dangerous, right? If I have 2 points, what if I confused feet and meters? Is my software smart enough to catch that? Because otherwise, if you see the error that's accumulated, it's a perfect fit. An inch can be a mile, depending upon your software. A lot of software will not let your scale factor get beyond a certain point. Other software may not do that. So you need to be careful about this. This also does not help at all with the verticality that we're trying to get out of the site calibration as well. Not only do we want to be good horizontal, but we want to be good vertically. If this was all I had, I would probably just hold the 1 point down there. I would check with the second point, and I'd let a geoid model take care of my elevations and the rest of it. On we go. 3 points. 3 points, we have now defined a plane. Anything flat will sit on top of that. The problem with that is it's a perfect fit no matter what. In the horizontal sense, if you look at the north error and the east error in my table up in the upper right, you'll see that we now have some horizontal error, because once I introduce that third point, it's no longer a perfect fit. It cannot scale everything to make it fit. And so it's got to distribute error around the network to find the best fit. And the software is very good at calculating this for you. But you can see in the vertical sense, I'm still perfect. And that's because I haven't got any redundancy in the vertical. Once I introduce some redundancy in the vertical, it will no longer be a perfect fit. As you can see right here, I've introduced a fourth point, and now I've got error to spread around in all dimensions, north error, east error, and vertical error. And I need to deal with it. I'm going to add another point, and I get even more error. So the software typically provides you with an opportunity to turn off horizontal components or to turn off vertical components of any of these points to find the best fit that has the least amount of error spread throughout the network. So in this example I show you, I've turned off the horizontal component of 5, and I've turned off the vertical component of 3, and voila, I've got very good error residuals here, and I would call this a good calibration. The final point I'd like you to recognize about this example is that all of my points are either at the edges or outside of the project area. And the reason for this is because of the error that I show you up there in the table. That is the maximum. And as I approach the center of the project area, all of those dimensions approach 0. So if I were to balance that whole thing right over the T of the project, I would probably have 0 error in my network all the way around. So you always want to be interpolating that residual error and not extrapolating. If I had all of my controls surrounding the words project area, then as I go out from that, I would start introducing more and more and more and more error as I approach the bounds of my project. A very important point. You can also see here that this does not require any knowledge of geodesy. The oblique stereographic projection is handled in the background. You don't have to have any knowledge about it. You can press the details advanced and go in there and find it. What I typically will recommend people do is look at the parts per million or look at the scaling. Parts per million greater or less than, plus or minus 80 is great. Scaling should have at least 4 or 5 9s or 4 or 5 zeros for that. I'm sorry, 1.0000 or 0.999. So NGVD, the earlier NGVD 29, which was our earliest modern vertical datum for the United States, was based on 26 tidal gauges around the United States. It was updated, as I said, when we adopted Old Man's Point as the point of beginning. That's way up past the northern tip of Maine. As it related out, we found that it was biased and tilted, and you can see this tilt that happens up there in the northwest, where it actually is wrong. NAVD 88 is wrong by that much, and it will be addressed coming up with NAPGD 2022, North American Pacific Geopotential Datum of 2022. Just as I was getting ready for this yesterday, I read an announcement from the National Geodetic Survey that their plans to do the modernization, the National Spatial Reference System, that they hope to have in place by December 31st, 2022, is unfortunately going to be delayed due to the current situation, but also with problems with getting the GRAB-D data that I mentioned earlier. So Geoid 2022 will be a time-dependent model, so it'll be regularly updated, and it will have a date attached to it so that we know not only is it Geoid 2022, but there will be some epoch that will be referenced as well. And then finally, I fudged here. In fact, this is a misleading slide, but this is the tool. In the survey community, we are going to have to transform coordinates on a regular basis between different datums. We're going to have a whole set of datum coordinates or coordinates that are based on the NAD83 system. And when the government does change to this NAPGD 2022 and the NATRF 2022, we're going to have to transform. And this is the tool that the NGS will use to allow you to do that. You can see I've taken a point in the San Fernando Valley and converted it from NAD 83 to the 2022 system. The problem with this slide, and the reason why it's deceptive, is because the NATRF 2022 choice does not exist today in the tool. It will be added to the tool. That's a Photoshop rendering of what it will look like, but today we do not have that ability to transform these coordinates as it's a work in progress. So, summary, GNSS assumes the Earth is perfect, and yet we know it's not. Gravity is affecting our elevations, and we use geoid models to define those differences. And again, for the umpteenth time, there's that formula: orthometric heights equal ellipsoid heights minus geoid separation. So that's my spin on GNSS elevations. I thank you. I see some red lights blinking, so I'm assuming there might be some questions out there. And if I can answer them, I'm happy to do so.
Well, thank you very much, Joe. It was very informative. At this point in time, we had a few questions come in that I was able to answer on some minor topics. And any other questions at this point on the session for Joe Sass? This has been recorded, as all of our weekly Ask Joe seminars are, and we look forward to any questions you may have in the future. You can email Joe Sass or myself, Joe Binder, at Joe_Binder or Joe_Sass at Trimble.com. Again, thank you, and have a great afternoon. Bye-bye.
Thank you, everybody. Bye-bye.